Okay, good morning, everyone. So, if you're not familiar with Autodesk, and I've learned this from working there, it's a massive company. It's about 14 billion market cap, about 8,000 employees. It makes design software, and almost no one knows that it exists. It doesn't get the name recognition of a Google or a Facebook. And that's largely because our first market was architecture, making computer-aided design. But now we've basically expanded into the design of many different things. But architecture is still very close to the heart. So this is probably one of the reasons why they asked me to moderate this group of folks. Now, I want to be clear. Humans aren't the only creatures that make homes and make buildings. You'll find examples across biology, things like termites building termite mounds, absolutely necessary for keeping the colonies going. Bees and wasps famously make their hives. Birds and nests. I'm Canadian. I'm a big fan of the beaver, and the beaver nests are remarkable. Large structures that actually change the course of many waterways. We have, as humans started to do construction, they really started to use a lot of materials that were on site, starting with things like brush, wattle and daub, incorporating animal dung as a reinforcing material. Soils and clays, thatch and straw, or here in North America, things like timber for log homes, and of course there's still a lot of timber construction used in the housing industry today. I'm delighted to introduce our three panelists who are really at the forefront of some of working with biological materials in construction, kind of next generation stuff. I interacted with all of you in different ways over the years. Ginger I met several years ago. Ginger Krieg Dozier is the founder and CEO of a company called BioMason. She's got a master's in architecture from the Cranbrook Academy of Art, a Bachelor of Architecture from Auburn University. She's really been focused for the last 10 years on how to grow materials for architecture. You've heard of, maybe we had Drew Endy up here this morning. He's famously known for creating modular genetic parts, BioBricks. Ginger is the first person I know that was actually making bricks with biology. Daniil Nagy is a designer and senior scientist with a design firm in New York called The Living. I should note that The Living was recently acquired by the office of the CTO at Autodesk, so it's now part of our umbrella of different services. He's also an adjunct professor at Columbia University and has expertise in teaching computational design and modeling of different structures, and also the application of big data and machine learning to urban environments. Welcome. And Joe Tarantino, hi Joe, is a fermentation biologist with a company called Ecovative. And you may have seen Eben Baer's TED Talk on Ecovative. It's using fungi, mushrooms, as a raw material, a biomaterial, again for making bricks, for packaging, and other things. So I want to start off with you, Ginger, because really I've had the longest relationship with you and have seen your work evolve. But tell me a little bit, for the audience, tell the people what you're doing, because it's fascinating.
Sure. So, firstly, it's really an honor to be up here with you guys as well. And so at BioMason, we're growing bricks, and we're using trillions of tiny workers, a bacteria that's responsible for creating a calcium carbonate cement. And the process starts with using sand, and then the sand gets inoculated with the organism, and then it's literally fed for a period of days until a solid brick is formed. And so I guess what's really been happening at BioMason is I started a lot of this research myself. I had a lab in my second bedroom initially starting off, but really growing it from, going from a lab in a second bedroom to taking it to a commercial scale where we have a team full of, material scientists and food scientists who are looking at how we start to scale a production where we can literally grow a brick, something that's so humble that, it's used in 80% of construction around the world. It's very exciting. I live a very exciting life. I'm living, the dream of that I've wanted, and really seeing how you can grow a brick, and it looks very much like agriculture. It looks like a greenhouse, and by which you literally feed these growing bricks that look like plants. So,
how long does it take to grow a brick?
It's a great question. It's a big milestone that we just made. Initially, it took over 10 days when I was starting out, and then we got the process down to 5 days, and now we're at 2 days. And we have some tests right now that are hoping to come out in less than 36.
And this is not a high temperature process where you're like firing?
That's correct. It's done in completely ambient temperatures.
I remember having a sample of some of your materials, and what surprised me was the density. It's heavy stuff. You were mentioning you're looking at how you might be able to make these things on site rather than.
That's right. It's something that excites us is looking at our supply chains and looking at how heavy materials are. And when you look at a conventional clay brick manufacturing plant, they're typically vertically integrated, meaning that they already own the mineral rights. They're already located where the clay is, and they take the clay from the site, mix it with water, and then fire it at 2,000 degrees for a few days. When we really started looking at manufacturing, it didn't make any sense for us to start a company whereby we would manufacture bricks and ship them around the world. We wanted to make the process possible so that existing masonry manufacturers could use this with some of the equipment that they already have. And so when you look at, all the embodied energy and all the cost that goes into transportation of materials, it makes a lot of sense to, look at your supply chains and look at what's the heaviest and where you really need to be located. So, just some examples that we've been looking at right now is aggregate. And we've been using a mineral waste. It's a waste fine that comes from the aggregate industries already. But I came from Dubai. I was there for about 7 years teaching architecture, and one of the most fascinating things to me was all of the sand. But more importantly was the fact that Dubai is the #1 importer of sand in the world. So it came to, okay, what can we do with the sand? So when I was working with the technology, it turned out that the process works quite well with the sand that you find in the UAE, for example. So can you imagine, being able to grow the bricks literally with the sand that's in the UAE, and how we're envisioning it is we can put the process in a shipping container, and think of it like an HP printer. You have the ink of the bacteria that goes into that, and it seeds the sand, and then you grow the bricks literally on site in ambient temperatures, of course.
Tremendous. Joe, you're making bricks as well. I know that. I know you're doing other things, but tell us a little bit about yourself, because I just learned that you actually came from a really interesting background. Tell us how you got to Ecovate.
Yeah, so I was formerly a winemaker here in the Santa Cruz Mountains. I was trained at UC Davis for such, and it was a great life. I love making wine. Really working with nature to create a product of that can be valued and appreciated for decades, right? And really appreciated that, and loved working with fermentations. But ultimately, making wine wasn't the end all for me. It was a great time, but there are more pressing concerns, and I decided to step away and really use my skills to help make things better. I'm also a rock climber, and seeing rocks, the lichen growing on the rocks, I remember seeing these big pieces of lichen and looking at them and thinking, wow, that's a lot like plastic. And so one day I searched grow packaging, and Ecovate popped up, and it was one of the most incredible things I'd seen.
For people that don't know Ecovate, tell us a little bit about what it does and how it does it.
So what Ecovate does is we really harness the innate ability of fungus to act as a resin and bond particles together. And the other great ability of fungus is to grow on lignin or cellulose feedstocks, which lignocellulosic feedstocks, it's the most abundant renewable resource on the planet. So what we do is we inoculate this feedstock with a fungus. The fungus acts as a self-replicating resin and bonds that material together. We can grow it in molds and make styrofoam packaging alternatives. We can also grow it flat and make insulation products. And now we're actually taking this material and pressing it with heat and pressure, and we can make engineered wood materials out of it.
Wow. And is there a particular product that you're working on right now that's kind of taking most of your time and energy?
Yeah, so my focus currently is really on the engineered wood, and we're doing this at our production and research facility in upstate New York, and small panels, and starting to actually make 4 foot by 4 foot panels, and actually making bent engineered wood material for chair backs, etc. And really the end game is to be able to do this at a scale where we can fit into a full-scale production facility, makes particle board or MDF, and so that's where my focus is taking our technology and how we can actually scale it up into a paradigm where they're making 4 foot by 8 foot boards every 4 seconds, and it's a lot of feedstock. It's 50,000 pounds of material an hour, and it's a lot of fungus. So how do we really take this principle, this concept, this technology that we've developed at a lab scale, that we've proven that we could start to scale it up, but how do we really make it explode and grow this material in a cost-effective and energy-efficient way?
Fascinating. I was just thinking of when I went through your production facility in upstate New York. It actually smells like you're walking through a forest. Really, it's amazing because there is so much lignin and cellulosic material, and then just that wonderful smell of the mushrooms growing, which is very evocative of being in nature.
Yeah, it's great. I love that aspect of it. I love the smells, and having been a winemaker too, I really pay close attention to the smells, and that can also be an indicator of when something's starting to go wrong, which invariably happens. Typically we strive to not have that happen, but that first sign, oh hey, it smells different in the warehouse. We need to change the conditions in order to optimize growth.
Tremendous. Daniel, tell us a little bit about what you're working on these days.
Well, my firm, The Living, we're a small design firm, 7 people on Brooklyn. We really like to say that we're interested in the future of architecture, but we do that through making functional full-scale prototypes today. And this is very important to the work that we do. Primarily, we're interested in the future of our profession as architects, what that's going to mean in the future. We want to impact the built environment of our cities, and through that impact have a positive impact on society. So we're interested in all the different ways that the future of architecture will be impacted by technology. All of us believe that biology and the ability to create new types of materials is a big part of the technology that will make that happen. But we're not biologists. We actually have been partnering with companies like Ecovative, who know the biology and the science part of those materials. What we're really interested in is testing those materials out at a truly architectural scale, and that's what we've been really focusing on. So particularly with the PS1 installation last summer, where we worked really closely with the Ecovative team.
So for most people may not know about PS1 here, so it's probably worth just mentioning it.
PS1, MoMA PS1 is a branch of the Museum of Modern Art out in Long Island City in Queens, and for the last about 13 years they've been doing this architecture competition to make a temporary installation in the courtyard of the museum. And there's about a few months time frame to do the design, and then you compete with about four different other firms to get this contract. At that point you have about 6 months for the whole design construction phase. You have 5 weeks to actually build a thing, and then it's up for 2 months. It's hosts a number of weekend parties,
massive parties, like 5,000 people
a day every Saturday this summer. And then it's taken down, and you have about a couple days to take it down. So this competition has become a really big part of the architecture community. It's a big kind of launching point for a lot of small firms. You get a lot of publicity. Of course, MoMA becomes a huge vehicle for that. But it's also been known to foster a sort of innovation in the architecture profession. And the firms that compete are really challenged to push the boundaries of what architecture can be today. Now, when we were shortlisted for the competition, we gave a lot of thought about what we can do, like what we have to say about the future of architecture and about innovation in our profession. And looking back at all the past years, there have been so much innovation in that competition, in the form, in the program, and we really thought, what could we add to this? We really thought about the lifespan, and we had this huge opportunity to make a statement about architecture at scale, so size really meant a lot to it.
This was big.
Yeah, so we designed a 40-foot tall structure. It's not completely enclosed, but it's reminiscent of what basically are the stakes in making a building, and this is really important to us. But we really wanted to confront the life cycle and take this opportunity of creating a permanent or a temporary structure that would really be designed to disappear as much as it was to reappear. And from the very beginning, we made our number one priority is to basically make sure that at the end of the summer, it was as if nothing had happened. So we would add nothing to the waste stream. And the disassembly became as critical a part of the design as the assembly. So once that was our goal, we found we were exploring new materials, basically the potential to create an entire structure that creates space, is at the scale of a building, but can basically disappear at the end of its life. We had this opportunity because the whole thing was only supposed to be up for 2 months. And we found EcoVeda's great product, worked closely with them to actually develop the bricks of the installation.
So it's been disassembled now and basically degraded in the environment?
Yes. So we also partnered with local composting companies in Queens. And this was a huge part of why we wanted to do the project. It's really good to have a vision about the future architecture, about new materials, but it's also really important to test it at the scale of architecture, because that implies a lot of aspects of the different industries that are involved in building that are the source of a lot of the problems we're having right now. So we think that we're really involved in innovation and technology, but it's really about our responsibility as architects. We take a profession like the whole building industry, which results in maybe 40% of the waste and the content of the landfills, and we think that fundamentally this is a problem that every architect should tackle. And we do it in a lot of different ways, but this idea of composting and new building materials is really important, but until we did it at scale with 10,000 bricks, we didn't know how much the industry can actually accept that. It was actually a problem to physically compost all this, even though technically it was very possible. The composters aren't at the scale to actually accept this material just from one
construction site.
So that's what we learned.
I think the idea of sustainability is so important, and just using some of these materials. But again, it has a whole life cycle. It's kind of bizarre thinking of your home having a life cycle and being alive. Maybe one day they'll have to be FDA approved, but it's pretty fascinating. Jinder sent me some numbers, and I was stunned. You said there are 1.3 trillion bricks made per year. And then you gave me some fascinating figures about concrete. Maybe you can share some of those just in...
Yeah. So, as an architect, looking at just the brick in its humble form used in over 80% of construction, I really started to take a look into it, and the team, we're all fascinated by bricks. So looking at the statistics, it is 1.23 trillion bricks that are made every year, and that's an estimate, and that's actually based on 4 years ago. So this number is increasing. And that many bricks makes 800 million tons of CO2 every year. And that's actually more pollution than all the airplanes in the world combined. And that's just bricks. Now you look at concrete. Concrete is much, much worse. We're talking about 4 billion tons. But one of the other statistics that I found to be quite intriguing was from the United Nations environmental program. And it mentioned that concrete was the second most consumed substance on Earth following water.
Wow. And people aren't drinking this, obviously.
And you're not drinking. Right?
But so it's really, it must be a heavy water user as well. Just makes
It
it
is.
hungry.
It's a heavy water user. It requires potable water to be used because if there are any other types of impurities or mineral interactions, there's a problem with the formation. So that's another reason that we started looking into supply chains very early and looking at what all can we use. I know there's a lot of waste streams for like cellulose materials for Ecovative's process, but for us it was looking at other types of waste systems, and the one biggest was looking at water. And this process can be used with seawater and it can be used with wastewater. And so that's something that's very exciting for us, but it's also very exciting for what it means that maybe bricks become a byproduct of making fresh, clean drinking water. So flipping it around.
Do you see the bricks actually being extended to being able to do concrete and make slurries and pour them in the molds?
I certainly think that concrete has had over 200 years of research, and biocements will need to do the same. But that's definitely the vision, is that we're making bricks right now, but really it's about an adhesive. It's about a binder that stitches these aggregates together in a cementitious solid form. So finding other potential uses, and we have some new developments that we're excited to share coming up soon that are really different than bricks. But certainly, cast in place, being able to pour this, in the ground, it's going to take some time. But I certainly think that if we don't do that, then we certainly have failed when it comes to looking at concrete replacement.
Joe, mushrooms actually, I understand, are one of the largest organisms on the planet because they really form these giant mycelial mats. Do you see being able to leverage this type of manufacturing outdoors as well, to actually, maybe put up frameworks and do this in larger structures, kind of on site?
Certainly I do. One of the premises that Ecovative operates under is, growing these materials where there's a regional ag waste supply and regional demand. Just because the shipping industry is, also a huge contributor to carbon in our atmosphere, and we want to minimize the amount of shipping that we need to do. There's a lot of potential, I think, to work with other organisms, in order to be able to do this outside, where, a myceliating substrate, that's going to become part of your building material, can just be done in a pile. And I think the best way to do that is through symbiosis, where you can, use bacteria and whatnot to really compost this material and grow your mycelium. And we have done, really grow in place situations where, one of our team members, he built a tiny house, and the walls are actually held together with mycelium grown in between the boards that actually make up the tiny house. It's just a proof of concept, but you can put the material into walls and have it actually grow and be structural.
Fantastic. I do want to take us a little bit into the future of these technologies. I think you're really pushing the envelope here on these different materials. Where do you see this going? Look out 10, 20 years. I've seen articles like people are thinking how you actually use materials on site, for example, to build structures on the moon. Would something like this work? And anyway, I'd just love a few moments of reflection before we open it up to some questions from the audience. Where do you see this stuff going? What do you dream of? Drew Endy was talking about growing a cell phone. This is a lot less complex.
Yeah.
But
something that we found super captivating when we were talking to everybody at Ecovative was this idea that, we started with a module because there's a lot of constraints now in terms of, should the thing keep growing when it's on site, and we did kind of a test. But one of the most captivating ideas was, even if you start with a module and you keep the thing alive and you start to stack them together, that actually the mycelium can grow in between the bricks and form this natural mortar. And we thought that was really amazing, right? I think right now there's issues about, even if we're not talking about animals, we're just talking about plants or fungus, the idea of literally keeping buildings alive is a huge issue, right? We were talking to some people that are like, well, usually you try to keep fungus out of the building. What happens when the whole building is actually made out of fungus? But just quickly, from our point of view, we're interested in a lot of this technology. We're also really interested about our profession as designers. For us, in terms of the architecture of the future, really think about what the role of the architect will be. And we mentioned this idea of life cycle earlier, and I'm really concerned about extending the role of the architect beyond project delivery. Right now, a lot of the waste that comes from buildings is the fact that the stewards of the buildings, the architects who are supposed to care about these things, basically stop their role at the time of delivering the project, and then who knows, right? Who knows who's taking care of it? I see that if the building will be living, then there's a huge opportunity for architects to basically be the stewards of that building, whether it's a doctor or a farmer.
Yeah.
Right? We're going to take care of those buildings.
And I see so much more programming and computational design coming into this to not only maybe engineer the materials going into the building itself, all of the management streams.
Yeah, that's the flip side, and we work a lot with computational technology, and basically it's around intelligence. I think when we think about these new materials, it's not just the biological systems, but it's also understanding how to work with those systems, how they age, and how they adapt over time. And we work a lot in computational systems as well. Basically, BIM, past project delivery again. Like, how do you manage the data of a building, not just in terms of sequencing construction, but also managing how that building ages into the future and how it dies in the end.
Fantastic.
Yeah, I think the idea of growing a cell phone is brilliant, right? And we've done research at Ecovative where we can actually grow the fungus in a liquid that has say copper in it, and it will actually assimilate that copper into its cellular network and act as a conductor. Right? So you
can grow your wiring for your home
you
as
can
well.
grow your wiring, your circuit, I think the potential to say grow a cell phone is real, but say instead of having a smartphone, you can now have a smart house, and really it's limitless at that point. What you can do.
I think, too, that I know coming from an architectural background and blending over into manufacturing and materials is that the role of the architect in terms of specifying the material, but also in designing the material. So, a little bit on the topic of mass customization, but being able to look through, the performance, where it goes in the building, and look at small engineering differences that make a large impact on the material itself. So, if we go back to bricks, for example, not all of the bricks have to be the same structural performance, but they can be changed and adapted. And I think it's very important, because I think that sometimes we gloss over these aspects when we specify materials and we just look at things aesthetically like color. But when we're able to really understand the performance and how they behave, and being able to choreograph, for lack of a better word, their performance over the lifetime of the building, I think is the next big thing.
Terrific. Let's take some questions. We've got about 7 minutes left. I'm sure there's a bunch of questions here. I'll just say keep your answers short so we can get a few in. Yep. So
this proves that the business plan, or the science fiction stories I read in the 50s were just business plans, and I didn't realize it. There was a story about a nanomolecular building that self-assembled itself. So stem cells can be repurposed, and there's a very, very clear pathway to take a stem cell and direct it. So do you see the next evolution of this being directed bioorganisms that are actually programmed to build in a certain way, rather than we can make a brick and then people put that together? So you're actually programming the material to just assemble the building based on programmed biological materials.
I think that's fair. Drew Endy used to challenge and just wake people up to the idea that one day maybe we'll plant a seed and grow a home. That's really wonderful. But I live in the redwoods, and I have to tell you, it takes a long time to make a large structure.
One thought I've had to that vein is, several 100 million years ago, there were giant mushrooms on this planet, 20, 30 feet tall, and mushrooms, they are so incredible in how they grow. If you go out in your yard, there weren't mushrooms there yesterday. All of a sudden, there's these mushrooms, and the reason they can do that is because they just absorb water, and they, the cells swell, so they don't have to actually go through division in order to expand. So the idea of growing a house, I like the idea of growing a mushroom and carve it out and use it as a living structure.
And if you're hungry, you could eat it.
Okay. Ellen Jorgensen, GenSpace. GenSpace loves this area. I mean, we had, with David Benjamin of The Living, he and I did the first iGEM team that had an architecture component in 2011. And in 2012, we partnered with another architecture firm, and we did a biomaterial out of Acetobacter cellulose. And we were part of the BioFabricate conference in New York in December. So we love this. And I teach at Cooper Union, and I'm teaching right now a biomaterials class, and we are growing. They're growing something out of mushroom mycelia, and we're doing cellulose. We don't have the bacteria for the bricks yet, but we love it. Anyway, the last questioner sort of stole my thunder a little bit, because David Benjamin, in talking to his classes at Columbia, says architects are late to the party a lot of the time. They're using tools that were designed not for architects, but software that was originally designed for engineers, et cetera, et cetera. So he challenges his classes to go to exactly the people, the synthetic biologists, who would have the ability to give you exactly what you want in your material, maybe eventually, and really knock on their doors and say, look, because they're looking for something to do that's meaningful.
Question.
The question is, I just want to put you on the spot. What one meaningful thing could each one of you get from, if your organism, because you're all working with natural organisms right now, right? Mm-hmm. If we could engineer one property into your organism, what would it be? Your wish list.
Well, I think responsiveness to humans and to the environment would be key. Right now our buildings are dumb, so more intelligence maybe would be good. And we're actually interested in this idea of distributed intelligence, not like the smart city in terms of this huge system that's all kind of integrated and will eventually break down. But we learn a lot from biology in terms of the distributed intelligence, the kind of automatic responses. And I think biology has a huge key to that. Right now we're working on computation and the computer as a stand-in, I think. And we're, how to work with kind of small-scale, bottom-up intelligence, but the future is really biology to give us that technology. I think having architecture that responds directly and immediately to its environment, and humans as a part of that environment, is the top of the list.
I agree. I mean, I think, if we're just looking at the organism component itself, we're still quite fascinated by how adaptive it really is, and how fast, and, the changes that you can make just on a classical mutation type level. But in terms of a wish list and looking forward is about speed, and the speed at which that adaptation can actually happen. So, it's not that, this one particular organism only works well in this X environment, but rather you can have different, types of environments with different extremes. So looking at environments that are cold, and yet being able to try to keep consistency in terms of manufacturing time, if by which that is an issue in terms of speed. So I would say, fast adaptation.
Yeah, I would say that for the most part, I feel like the engineering's already been done. We get different material properties from each species of fungus that we work with. Some are flammable, some are fire resistant, some are hydrophilic, some are hydrophobic, a wide range of material characteristics. And, we have a number of species that we work with, and different members from the team, we go out and we forage and we find fungi that literature has told us are, going to give us interesting characteristics, or that we see have interesting characteristics. There's an estimated 1.5 million species of fungi. So again, the potential is limitless for, the material characteristics that are already there in nature. It's just a matter of giving them the right environmental conditions in order to grow, and that's just fungi. Shells, that are produced are, it's an incredible material. How can we use that? So many organisms, they make their home with these great materials that we can really just appropriate as opposed to having to change them.
I think we have time for one more question.
Hi, Robin Tang, McKinsey & Company. I just want to say thanks for describing some absolutely fascinating technologies. I wonder if you guys could comment on the applicability of technologies like these to emerging markets. Ginger, you sort of alluded to sustainability challenges, and it seems that developing countries could leapfrog a lot of these problems potentially, but really only if the price point, if the cost, if everything fits for them. Could you tell us about that?
No, that's a very great point. I think for companies companies like this is that when you're starting off and you look at, the lowest hanging fruit environments. Like when we first started working with this technology, we were in an environment where we had, all the raw materials available to us, but really looking at markets that can accept this. So you brought up a really good point. The best way to prove out new materials like this is to go full scale and to install them. So that's actually what we're doing right now, is we're working on that initial pilot. So putting it out into the world. And, simultaneously in the background, there's a lot of different types of optimization that comes into place. So for us to be able to build ourselves up in a robust level, to be able to tackle those challenges, because that is what keeps us motivated and what keeps us going every day, is thinking about, where is this going to make the biggest impact? I mean, certainly it's going to make an impact here, but where else can it make a big impact? And you're right, it comes from, areas that do manufacture, almost 72% of some of these products. So I think that the short answer to that question is that we need to prove out ourselves, and that's what we're doing and what we're successful at right now, is being able to manufacture that so that we can go out and teach others how to do it.
Good. Well, we're out of time. Thank you very much for sharing your work with us.